Alright, hi. In this video, I'm going to be, just going to turn down my volume for a second. In this video, I'm going to be coding what we discussed in part one. Those equations that we went through are too difficult to solve by hand, so we're going to be putting them into Python, Google Colaboratory, and I'll explain it as I go. And then we will be able to solve for our unknowns of total volume and final temperature in order to get 0.3 moles of water in the vapor phase in the system that, again, we discussed in part one. So first things first, up here, I already typed out all of these imports and whatnot. Doesn't really have to do with the actual content of this video, but this first part brings in dot map. Second part, I've got it written right here. This is a path to CHE model imports, which is Dr. Ko's code that contains information about different compounds, elements, stuff like that, and we're going to use that in here. And then all of these imports include JAX, which does automatic derivatives, dot map, which stores values, pandas, which does data arrays, and then more of Ko's code down here like VSC and range, which it's the compound element information that I'll further discuss, and also minimize function that we're going to use to find our values. Okay, so the first thing that we're going to do is type it, and I'm going to talk about it. Now this is Dr. Ko's code, and it's going to contain all of the information that we need for these equations for argon, oxygen, nitrogen, and water, because those are all the different compounds that are in our system because of air and water. So I'm gonna do props. We can do nitrogen. Oxygen, carbon. Oh, I can't forget to put the apostrophes around it, and water. Okay. So that brings out all the information that is in Ko's code, so we don't have to manually find it and input it ourselves. Very nice of him. Oh. Okay. So next we're going to define our model. So C is going to be a combination of adjustable variables, and then R is going to be intermediate variables that will be stored in dot map. Okay, so I'm going to start out using the, and this is part of Dr. Ko's code. It's already going to have the value for me, but I'm going to use Antoine's equation technically to find the partial pressure of water as we discussed in the first part. So we'll call this partial pressure of water is going to be, and this is an intermediate value, so we're doing R dot and then P of water. And then P dot signifies this P up here. So vapor pressure is PVAP. C dot T, which we will define down the road, it's going to be a specific temperature value. And then index 3, because Python index 0, 1, 2, 3, and our 3 here is water. Oops. Again, let me just type something out, and then I will explain it. Okay, so what this is saying is the volume of, this is our, again, we discussed in part 1 the volume of the vapor phase, so that's going to be the total volume minus the volume of the water, which, again, these are all values that we're going to plug in or find either by an equation or straight value down the line. Because if you remember from the first video, total volume is one of our unknowns, but we find the volume of water using the mass and density. So now we're going to do the moles of air, which again is an equation that we solved for in part 1. Is going to be equal to the pressure times volume of the vapor phase divided by gas constant, which we defined up here, I forgot to mention. Gas constant times temperature. Okay, so then the next thing that we're going to input is the moles of water in the vapor phase, which is something that we know, but we are solving for two different things so that we have a certain amount, which is 0.3 moles. Okay, so we're going to do partial pressure of water times the volume of the vapor phase divided by RT. Sounds good. So let's do R dot W and that equal to the partial pressure of water, PW, times the volume of the vapor phase, R dot divided by RT. Okay. All right. Now we're going to do the pressure as in the total pressure is equal to the number of moles times R times temperature divided by the volume of the vapor phase. So this is the partial pressure of air, because again this is for total pressure, R dot P, plus R dot partial pressure of water, which the equation is for up top. Okay. So now we are going to add in our constraints. So we're going to do a pressure constraint and a number of moles constraint. It makes it so that the pressure we calculate is equal to the desired final pressure, and the same story for the number of moles. So P underscore constraint for pressure constraint. Scroll down a little bit. Is equal to C dot P underscore F pressure final. Okay. And then our number of moles of water. Constraint. And again, these are some values that we will define in a second. They're all just variable names right now. Okay. So as discussed in part 1, these constraints are what's going to make the final pressure equal to 200,000 pascals and the number of moles in the vapor phase of water, 0.3. Okay. So then we'll do constraints. Okay. So now we've got our entire model defined. We are going to define all of those values, and part of this is that dot map I was talking about earlier. So we'll do C, and that's what all those C dots are going to be. C equals dot map. Okay. And then I'm going to do C dot. So this is the mass of the water, which is equal to 1 kilogram. So we'll put in the units, why not? And then we need our total volume, but this is just going to be a guess because we don't actually know our total volume. and that would be in liters. Or no, that would be in milliliters. That's 10 liters. And our initial pressure is equal to 100,000 pascals. And the units are unnecessary, obviously, but I'm just adding them in there. Makes it look nice. And then our final pressure, C dot, final pressure is equal to 200,000 pascals. And then our initial temperature was 298, which again is room temperature in kelvins. Okay, so there's all of our given information from the problem itself, but we also had the number of moles desired, so that was 0.3 number of moles desired water in the vapor phase, which we define at the top as W_N desired, and again that's equal to 0.3 moles. Okay. And then our temperature values and our volume values are going to be our adjustable values. Okay, so C dot T, because again, what we are trying to find is the final temperature and total volume. So T dot T is going to be a range. And our first guess can be like 350. Our lowest guess, or our minimum value, would be like 250. Pretty cold. And then our top one can be 400. Okay. So again, in this range, it's the first part here is like an initial guess to start with, because again, the function that we imported up there that we're going to eventually use is going to minimize this to find what TF final temperature actually is. It's going to do the same thing for total volume. So this is the initial guess, this is the minimum value it could possibly be, and this is the maximum value it could possibly be. So we're going to do the same thing for total volume. That arrange as well. And you start out with 0.01. You can't have a volume that's less than 0. And then we'll make our max 0.3. Okay. So now, that VSC function is what I was just talking about. That's what's going to do the minimization to find what these values are. So VSC equals VSC, and this is something that Dr. Ko wrote. Again, C and model it already knows for me. And then we have to do VSC dot solve. Okay. And let me look through this really quickly. One of the first things that I noticed is that I wrote this variable name incorrectly, which is something that I am guilty of often. So it needs to be an underscore vap underscore desired. I'm gonna try to run that. Okay, we still have an issue. R.v underscore vap. So it's something with this. C.v total, we have that. Let me check this out as well. So I realized that I left out a very fundamental aspect of what we're doing. So basically, let's look at the error again. It shows the issue with this line, which is right here. And the reason why is because, as I said when I was writing it, and in part 1, to find the volume of the vapor phase, we needed to subtract the total volume, or we needed to subtract the volume of the water from the total volume. And to find the volume of the water, we needed to use the mass and density, which I never typed in. So I'm going to do that now. Do that right here. So we'll do that by doing, so our C dot the volume of water is equal to the mass divided by density. And density is something that, again, Code has stored for us in one of his codes, so we can use that. And then our mass is C dot W underscore tote. So P dot rho is, since rho is the Greek letter for density, do that of dot, and we want that of water. So again, that was index 3. Okay. Now this should spit us back some numbers. Okay. So those are unnecessary, really. But what we want to do now is we are going to this is basically showing that it has minimized the function and it has found our total volume and final temperature values. And this is like the accuracy. So to display that, I'm going to do VSC.VDF, and this is going to be a data frame of our adjustable variables. So the final temperature and the total volume. So this is what it is. The final temperature is 365.7 kelvins, and the total volume is about 12.8 liters. So we found it. And then just to show the intermediate values, I'm going to do VSC.RDF. That should, yeah. So this gives us a data frame of our the intermediate values, which we can also kind of verify our results because we can see here that the final pressure did end up being 200,000 our moles of water in the vapor phase is 0.3, and then here are the other ones. So, yeah, thank you for watching, and yeah, here's the code.